I really don't think I could watch you guys struggle much more. Not all of these things are necessary. So what you have to ask yourself is, what is doing the orbiting and what is being orbited? That's an important question, right? Yesterday it was the spaceship orbiting the Earth. Today it's the Earth orbiting the moon, or the moon orbiting the Earth. Which one is it? We're looking at the moon orbiting the Earth. Now, to be honest, the moon is really big compared to the Earth. That's kind of part of the reason why I wrote the numbers up there the way I did. Do you notice that the radius of the Earth is 10 to the 6th, and the radius of the moon is 10 to the 6th? And the Earth-Moon distance is 10 to the 6th. I did that on purpose. That way you can see the relative distances. The 10 to the 6th part makes it difficult to understand the scope of the size difference. But if you ignore that, the Earth is 6, and the moon is, just a little over 1.5. That means the moon is about a quarter of the size of the Earth, right? We can make that relative comparison. The 10 to the 6th, that just gets in the way, so kind of ignore it. Similarly, 384, well, that's several hundred times 6, isn't it? Well, maybe 50 times 6. We're talking about the distance between the Earth and the moon. It gives us a relative comparison. So like when we were just doing that just a minute ago, that is probably too small for the actual size of the Earth that we were using, because that's smaller than a quarter of the size of the Earth. Would you guys agree? And we certainly weren't 50 times the radius of the Earth apart. But that would be more appropriate if we wanted to do a true comparison. Does that make sense? Because that's what these numbers allow us to do, make a true comparison. If we really wanted to make it real, and we could have. You're going to help me again. You get to stand here, though. What would we say? The radius of this is just a little less than a foot. Wouldn't you guys agree? We need something that's about a quarter of that. Maybe I have something. I think this would be about the right difference. So I need to go 50 radii away from, so I think this would be a better comparison. Earth, moon, because about a fourth compared to that. But I would have to place this 50 radii away. That's 50 feet. So every case is about 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. This would be a good representation of the Earth-Moon distance if that were the size of the Earth. All right, these are just the numbers. You guys seeing that okay? So there's a lot of stuff in between. Wouldn't you agree? So all of our things that we have tend to be of weird scales. So if we're trying to get it accurate, this is how I should have done our demonstration a minute ago. But I would have had to place the sun at the mall. Because of the right scope and scale, the sun would have to be that far away for us to be able to get the scope and scale more correct. Thank you. I'll leave this up there. This is a lot more fun. I do have flashlights on my Crocs so I can see in the dark. Don't you have flashlights on your Crocs? I need some of yours. How do you see in the dark? All right, so let's handle this calculation because I am frustrated by the things you don't know. So you're a little smarter today. Nothing that has to do with your next test, but a little smarter today. We are talking about the Earth and Moon system. So Earth, Moon, and they are far apart, but we're looking at the orbit of the moon around the Earth. So this is the orbital parameters we have. Looks like the mass of the Earth is the thing that's being orbited. And the mass of the moon is the thing that's doing the orbiting. I did give you 3 distances. Probably one of them is the one to use. We need the separation distance between the Earth and moon to be able to calculate the force of gravity on the moon and the force of gravity on the Earth. Did I provide you with the separation distance between the Earth and the moon? All right. Probably this one is the one we got to use. And you need the radius of curvature of the path of the moon. Can we say that the separation distance is also the radius of curvature? We're going to have to make a choice. I think today we'll say yes, and maybe in the future when we are smarter, we'll say no, because the actual place that they orbit is right about there. They orbit at a spot between the two. That's because the moon is really massive, and so they orbit at what's called the center of gravity between the two, or the center of mass. And that's where they actually orbit. If you've ever thrown something, like something oblong or not a ball, you'll notice that if you throw it and it spins, it doesn't just spin about its middle, it spins about its center of mass. So that's why it might spin awkwardly. So we're going to treat it as if it's spinning about the middle of the Earth, because that's within your capabilities right now. So let's start from the beginning. This will be the unbalanced force that's acting on the moon. And because it's an unbalanced force, it causes an acceleration, but not just any acceleration. It causes a centripetal acceleration. Now we could use that combination to figure out the velocity. Right? That's our first substitution. Now, stop here before you go any further. What do you think you should use for M1? Okay, so if M1 is the mass of the Earth, what's M2? Mass of the moon, okay. What's this M? See, we have some disagreement. But that M is the thing that's doing the orbiting. It's what you say is going around. It's experiencing the unbalanced force. It has a centripetal acceleration. So what do you think that's going to be now? The moon. Notice, as I said yesterday, the mass of the moon cancels. The thing that's doing the orbiting doesn't factor. Its mass doesn't factor in. Now, I asked for the time. I'll point out, this won't find you the time. This is going to find you the velocity. Now, you could find the velocity and then find the time, sure. Or you could substitute and get rid of the velocity and just have time. I want time. You choose which way you want to do it. But because I want you guys to be better people, I'm going to show you that you could probably do this in a single step if you did this substitution, as opposed to finding the velocity first and then finding the time from the velocity. So I want you to be better. So I'm going to do it the way I just suggested, but I'm going to knock out that R first. And I'm going to have mass of Earth times G divided by R equals, but instead of V squared, I'm going to put 2 pi R divided by T squared. Oh gosh.
No, I hate that now I understand.
I hate that now I understand. You have to get T by itself if you want to do it this way. And I'm willing to do it this way. But getting T by itself, I'm going to have to square the top and bottom, cross multiply, and then isolate T. Do all those things sound like things you can do? Well, let's see. That's a lot of things. So I'll be careful and do them in many steps. Step number 1. Now cross multiply. cross multiplied. And now solve for t. That's a lot to do. Do you think you can do this? Try it out. I mean, I could put all the numbers on there. I don't want to. And for you guys, you should probably like calculate the top first. You got that cube in there. There. So quiet.
No, there's two twos in a row. What is it? Yes.
Now, this is successfully calculating the period of an orbit. You could have stopped at any one of these stages earlier to figure out the velocity to be in that orbit. We often do this in reverse. We often look at celestial objects and measure their period by observation and use it to figure out the mass of those objects. So this has been used in other ways. We could have at any time taken this and solved for the mass instead. Understand, and this is critical for what I want you to know, this value for G, we believe, is the same everywhere in the universe. So when we make observations of planets that are far away, maybe in other solar systems, or we observe a star and we see it wobble, well, we know that it's wobbling because something is orbiting it. If we can measure the period of that wobble, then we can probably use it to figure out the mass of that star. This is how when they talk about the size of other stars they see in the solar system, they use this to figure it out. But it's important to know that this is what we feel is universal, that we can count on the fact that the G is the same there as it is here. Yeah.
How do we find like the radius? For, like...
Radius is done using a different procedure, but they measure the arc seconds of angle difference between one side of an object and another, and then extrapolate how big that object has to be by using triangles, basically. Imagine if you're looking at something that's... my expectation is that with given information, you should be able to calculate the three properties of an orbit that we described. The velocity of an object in orbit, the period of time that it would take that object to do the orbiting, and work backwards from an orbital bit of information and maybe figure out the separation distance or the mass of the object that's being orbited. Again, it's important for you guys to be able to do this set of steps. First substituting in using Newton's second law, and then dealing with the velocity. I want you to be able to do all of those things. However, not one of you has brought up the fact that this is not 28 days. You brought it up. Why isn't it 28 days? So, most orbits aren't perfectly circular. They're elliptical. In fact, we use a word to describe how, elliptical-like an orbit is. We call it the eccentricity of the orbit. An eccentricity of 1 is a perfectly circular orbit. But most orbits have an eccentricity that is less than 1, and that measurement is basically the ratio of the semi-minor axis to the semi-major axis.
A circle has a 1-to-1 ratio, but the smaller, or the more elliptical it is, the smaller this is compared to this one. So most orbits for the inner planets are like in the 0.95s, 0.98s. They're very close to circular. But you start getting to the outer planets and they become more and more elliptical. That's right. Weird schedule today. All right. Very far away, assuming it's circular, and you're observing it from a point that's really far. So they measure this amount of arc-second difference. Arc-seconds is another angle type measurement, and it's for very small angles. But they can do that to kind of predict what this size has to be. They also then have to also get an idea for how far away it is before they can do that. So then they have to use something else to figure out what they think is the distance away to be able to use the arc-second method to determine how big the object is. Does that make sense?
Yeah.
Determining how far away it is often is by looking at the shift in the color of the light. They can use some information about that to figure out how far away it is. And there's a few other methods that they use to determine distances for objects that they can perceive through a telescope. So it's a lot of combinations of stuff to figure these things out. It's not as straightforward as it seems.